second talk is about adaptive optics and the use of liquid crystals. So Restaino, who was supposed to give the talk, couldn't come, but Ty Martinez, also from the Naval Research Laboratory, will give this talk.
Hi, I'm Martinez. Going to be talking to you about adaptive optics and use of liquid crystals. Sergio, I've been working with probably about 10 years now. I was able to come, so I got coming soon. So I'm going to give you a brief introduction to the problem and talk about atmospheric turbulence, and then go into adaptive optics and classical adaptive optics, and then talk about liquid crystals and basically the test bed that we have and some experimental results in that. Right, so the first thing basically is the limit of resolution for a telescope basically is given by lambda over d, where d is the diameter of the telescope, lambda is the wavelength that you're working with. Basically, for just to get an example, like for the Keck telescope, which is diameter of 10 meters, you can get about 5 nanorating resolution, which is about basically a man standing on the moon. But the problem with it, right, is that not only is true in vacuum. Basically, if you wanted to actually get that resolution, the atmosphere is in there introducing aberrations, not letting you get that resolution, the full resolution of that telescope. So you'd say, well, why do they make telescopes that big? And well, the main reason is that you get more light collection also as you get for the larger apertures. Alright, so basically if you have a lens or a telescope, basically there's a relationship between the aperture and the image that it'll produce, and it's a Fourier transform relationship. And basically, so if you have a flat wavefront coming into your telescope, then it'll produce basically this nice airy pattern. And then, so you can have the area pattern. The other way you can look at it basically is, you have a point source coming in, basically you get this basically nice sharp point that you're looking at. Or you can also look at it, what the optical transfer function of your system would be, basically what spatial frequencies you can transmit through your system. So something that's varying, quite a bit, basically, and that again is dependent on your aperture. Basically, it's 0 to lambda, so basically the cutoff frequency is given by that. Now, basically, the effect of aberrations on your system basically is going to spread that point spread function. It's going to broaden it, or in terms of the transfer function, right? It's going to decrease the transfer function. All right. So basically, when you have aberrations, basically it's this phase term that gets introduced into your system. It's going to decrease those aberrations. And adaptive optics basically is trying to introduce another phase basically there that is exactly opposite in sign of this one to cancel it out, so you can get basically the nice, good imaging again. Alright, sources of aberration basically you get are thermal distortion, mechanical distortions basically, it's vibrating, or if you have wind hitting your telescope and it's caused buffering, so you get vibrations. And then the big one basically is atmospheric turbulence. Alright, now, basically what does this do to a system? So here we're going to look at an example where basically if you have a 4-meter telescope and you're looking at basically visible wavelengths and Arnaud I'll explain a little bit later, but basically it gives you an indication of how bad the atmosphere is. And under those conditions, basically, you ideally have 10 to the minus 7 gradient for your diffraction limited imaging. However, with the atmosphere, basically, you end up going down by 2 orders of magnitude in resolution. All right, here's Arnaud. Basically, there should be an equal sign there. So, basically this parameter called the free parameter basically essentially gives you the size of an aperture that you could have, that the only aberration that would be present would be tip and tilt. So if you have an aperture that size and you looked at it and you have a tip tilt correction on there, you get diffraction limit imaging. The problem is if you go to a larger aperture than that, then what happens is that it degrades the overall imaging, because now it's an aperture larger than that. What happens is you get different, essentially atmospheric cells inside that cause aberration to change. So you can't just correct it with tip tilt. You have to use a higher order device to correct it at that point. Other parameters of the atmosphere is tau naught. Tau naught basically is a Greenwood time constant. It basically says how fast basically the atmosphere is moving, how turbulent, how quickly it's evolving. And another parameter that's important is the isoclimatic angle. And this angle basically is the angle over which you could have two point sources or two objects coming in at you, and they effectively see the same aperture. Beyond that, the atmosphere would be different, so in that case you have trouble actually being able to correct it. Alright, now here's basically, I think it's the first 70 Zernike Polynomials. This is a basis set, orthonormal basis set that people like to use because you can take individual ones and add them in and out of your system or characterize your system, and since it's orthonormal basis set, one doesn't affect the other. Right? And they're basically the ones shown here, basically the first few you can think of Seidel aberrations or aberrations that most people can think of. Basically the first two are basically tip and tilt, so tilt on one axis and tilt on the other. And this is defocus. And then you get stigmatism in one direction, stigmatism in 45, and then coma, and so on. Basically this is a basic cartoon of a radio system. Right? So basically you have your distant object, or basically a star, basically a point source at the end. So it's going to get a spherical wave as it comes, as it travels through, it evolves. By the time it gets to us here on Earth, it's a plane wave essentially. All right. Now it has to go through the atmosphere, basically. With, and what you can think of is these little spots here, basically, are acting like little wedges. And the way the atmosphere, what's going on with the atmosphere, right, is that you have temperature changes in the atmosphere, so it affects the density. So the way you can think about it, what's going on is that you have these little wedges that are deviating the beam as it goes through it. So you end up with, instead of a nice flat wavefront, you get basically the wavefront has been delayed in spots and tilted in spots, so you get this aberrated wavefront instead of coming into your telescope. Right, so you come into the primary, the secondary, and you come over here. Basically, what we have here is a turning mirror and then a lens, basically that reimages your pupil, basically your primary, onto a tip tilt mirror. And this tip tilt mirror is going to get rid of basically the overall gross tip tilt of the atmosphere, which is a large part of the aberration. Over 80% is in just that tip tilt. And then the next thing is it goes to deformable mirror, and there you can basically adjust actuators on the mirror to correct it with the opposite of what the atmosphere is. And then the next thing we have is the wavefront sensor. In this case, I put a Hartmann wavefront sensor, which is basically going to sense what the aberrations are that are present in the system, and then be a computer to calculate what it needs to correct, and feed signals to the deformable mirror and to the tip tilt. And then, so when after you've gone through that, and then the correction, you get your final images corrected at that spot. So it's really like giving this history of the adaptive optics. And the first thing being Archimedes bringing rolling ships, which if you watch different shows like Mythbusters, there's some debate of whether you could actually do that or not. But anyways, there's this story basically the first use of optics for military applications where we're using the sun and a mirror basically putting the enemy ships. Then basically in 1730 basically published works where he talked about basically the air causing problems for a telescope, and you have to go to basically the mountains to be able to try to get away from the atmosphere as much as possible.
I have a question.
Yeah.
The first event, was that really true or was it a bummer?
I mean, I guess there's some data on whether that's actually true or not, and whether that actually did happen. But there are stories of it.
Would it have been possible?
That's what I said, like in Mythbusters. I don't know if you've ever seen that show. Basically, they've done some stuff, and you can potentially, if you have enough mirrors and enough people correcting, they did do it, but it's difficult. Alright, and then let's see, in 1953, that was basically published talking about using an iodophore to basically introduce perturbations and try to eventually statistically get it where you can correct for the atmosphere. And then in the 70s, basically DOD started to classify work, and in 91, basically they declassified the work because basically astronomers were starting to reproduce it. Alright, so what are some applications? Basically surveillance in astronomy, then laser propagation for laser comm. Also, it's found applications in ophthalmology, basically medical imaging. And this is basically showing a person's retina. And basically, these are the standard images that you get. And this is using a 37-element deformable mirror to correct. And this is a 97, so you can start seeing the cones on the person's retina. So just to look a little bit more in detail, so from your telescope, so you have this aberrator beam, it comes in, it hits this deformable mirror with actuators. What you're trying to do basically is put the exact opposite on here to correct for these aberrations. And the way you basically measure what errors you're getting is with a wavefront sensor. And again, just this quick schematic about the Hartmann, I'll explain the way that works a little bit. But the idea is basically that you measure that wavefront, and then you use a computer constructor to feed exactly what you need to correct that to a deformable mirror. Alright, now for the Hartmann wavefront system, what it is basically it's an array of lenslets. Alright, and so you're breaking up basically this aberrated wavefront. And if your lenses are small enough, basically all that it looks like to this individual lens is a tilt. And basically, so to this lens here, basically that just looks like a tilt. And you can measure how much it's deviating from basically if you have a flat wavefront coming in, they would be just where the black spots are coming to focus for the rays from the black hole. But because of that tilt, they end up getting them shifted. Right? And by measuring that shift, you can get what the local tilt was for the wavefront, and you can get an overall state of what the wavefront should have been. And this is a picture, and what we have here is basically this was actually a reference beam, and then we put an aperture on the other beam, the second beam coming in. So these spots here on this large beam basically are where the spots should be ideally formed for a perfect wavefront. And then if you squint your eyes, I think you can see that there's another beam, basically a smaller one right here. And basically those spots aren't exactly lined up. If they were lined up exactly, they'd be right on top of the other spots. But because there's some aberrations on it, they aren't lined up. So the goal basically is that using a deformable mirror, then you can force these spots to go to where they should be. And this is basically showing data from an experiment that we did where we were on a telescope at a central obscuration. Basically, and you can see, if you look at this one, you can see that the spot is wandering around a little bit. As the time evolves, it's going a little bit of a circle and showing you that basically it's measuring that localized tilt that's going through the atmosphere. All right. Other wavefront sensors that are used, basically, there's it's called a phase divergence curvature sensing. And here, what you do instead of measuring local tilts, what you're going to do here is you're going to measure local curvatures. And the way this is done, right, is basically you're going to look at two different planes, right? And the way you do this is you're going to put a beam splitter in your system, and basically you look at one plane and you look at it as also another one. So you have basically two separate cameras that you're looking at, and basically you can see that this one here basically is converging. So the intensity from here versus here is going to be less. Right? And here, basically, it's divergent, so the intensity from here to here, basically, this one's going to have more intensity here. So when you take the difference of those two different images, you get intensity differences, and those intensity differences basically tell you how the curvature is varying in your system. And from that, you can get an idea of what your overall wavefront is doing. And what people like to couple that with is with a MEMS type of device that I'll talk about a little bit later. And the reason is because with a MEMS device, what you get is you can get this nice relationship where the voltage that you apply to the device basically is just related proportionally to the square root of the difference of the intensities of those two beams. So it ends up being a nice, real simple relationship that you can do with those types of mirrors. So for deformable mirrors, with basically the classic idea that people have used basically is using segmented systems where you have to be able to match your wavefront. You have a bunch of segmented ones that you have piezo's. Basically, you can adjust the piston, or they also do where you can put two actuators on the back so you can do the piston to tilt to do the deformable mirror to match your wavefront. Other technique that's used basically is continuous phase plate, where you have these actuators and you can shift the mirror around again. And another one is this electrostatic membrane, where you have a very thin membrane here, like 20 microns thick, and then you have actuators on the bottom. You can apply voltage, and by applying voltage, you basically get the mirror to deform down to the of the actuators. Then another type of deformable mirror that's used is a bimorph, where you have piezoelectric material aligned in two different directions, and by applying the voltage there, you can cause local deformations as well. Now, basically, with those you typically get with the faceplate type of and MEMS type of mirrors, you get an influence function on the device. So the actuator is right here, but it actually affects the mirror at other locations. While if you use like a liquor pistol electrically addressed type of device, the influence function is localized to just the LC itself. And then, so you did simulations and just showing basically you have, if you have the Aberrator wavefront, which is the one shown here in orange, how many actuators do you need on a mirror with the influence function, basically, to actually be able to correct it well. And so, and what he did was he used ones basically that were commercially available, a 19 channel, 47 channel, 37, 57 channel device, and then showed how well you could correct it based on those influence functions. Now, with classic adaptive optics, the way most people think of it, basically the biggest problem there is the cost. And it's roughly $5,000 per channel. So to get a device like you shown here, with 600 channels, basically, the cost of $3 million. So for most people, it's beyond what their budget is. So what Strehl's been working on is trying to figure out different ways, different approaches. You can use different types of device that bring that cost down. And here's just an example. Basically, this is a standard deformable mirror. You can see all the cables coming into it, basically coming to the piezo elements. This is got 120 basically channel device. Basically, it's has this large rack to run it. Whereas he's looking at using MEMS type devices or liquid crystal devices, which the cost per channel is a lot less, and the weight of it is a lot less, and the power consumption is a lot less. So the liquid crystal devices are basically, you can get the number of corrective elements also extremely large. Like that. I mentioned. Actually, that one later on. So, let's see. The liquid crystal devices, you can get a large number of elements. Reliability is really good. The other interesting thing with the liquid crystal devices is these ones. One of the things Sergio was talking about is not mainly about electrically addressed. However, with optically addressed ones, you can use real-time holography, which is nice because you get to eliminate the use of the computer in the system. And you see the other devices we've been looking at is MEMS devices, which again you can get fairly fast killers type stuff, and the cost is a lot more easier. Right. And then here's some examples of some of the devices that we've worked with, showing what throws you can get with them. So basically, essentially, how much aberrations you can correct for, and then showing what speeds they can operate at. Right. And then as far as the liquid crystals, basically what we want to do right through the phase modulation to do the correction. So the type of devices that we primarily use are pneumatic devices. And the biggest problem with the devices basically is the switching time. And the speeds, like the device that Sergio was able to use on a telescope, the way they got the speed up was actually using a dual frequency device, so you could drive it in both directions to get the speed up. And this is actually some data from inside the lab where we're aberrating a beam and finding the correction. And this was using a dual frequency spatial light modulator. So it'll go basically right now the loop's closed, right, and then you can see when it's not closed, and you can see the correction that you get with the device. And basically we improved basically the closed loop Strehl ratio is 0.34. Strehl ratio, we have to include that. Strehl ratio is basically the ratio of aberrated to unaberrated intensity at the center. So basically, if you had an unaberrated system, you get a value of 1 for the Strehl ratio. As the aberrations go up, the Strehl ratio goes down. And so for this one, basically, the Strehl ratio was about 0.08, and we were able to get about 0.34. Right. As far as the device, this was the dual frequency device, which was made by a metal art under SVIR. And the diameter of this device was, I believe it was an inch aperture. And then some other devices that Sergio had developed. This was a large format device. Basically, this one had 128 total elements in it. This device here actually has 128 by 128 elements. And its aperture here was about 5 inches. And then here again, this was actually done on a telescope, and he's showing correction using this liquid crystal device of a binary satellite. This was open loop and this was closed loop with the device. Right. And then this is the other device that we've been primarily working with. This is a MEMS mirror. Basically, it has a very thin membrane with electrodes underneath. You apply voltage, and it forms this membrane down. To use this device, you have to use it basically with a bias curvature, and then you can, by changing voltage here from that bias curvature, you can get effective changes in the waveform. And this is showing an interferer coming off of one of these mirrors, and you can get basically, for people who don't know, the easiest way to think of it is it's a topographical map of the mirror itself. So here, since you have these rings like that, basically you get this basically deformed shape, or concave shape on the surface. And then here it's basically showing the influence function for that deformable mirror. These are calculated and these are measured. And basically you can see, main thing to notice is that these are for different actuators. So when you have one actuator activated, it does influence the mirror out to the next actuators. Here basically are some demonstrations basically on telescope. This one was at the Naval Auditorium, looking at again from 0.037 in Strehl to 0.22. Open loop, you can see it's spread out. Closed loop, you get a tighter spot. Same thing here. Now we're looking at an extended source though. We're looking at the International Space Station with the low frequency LC device. Here, open loop and closed loop, and same thing. Well, actually, this was looking at a different satellite news device. Right, and then the whole idea with these small AO systems that instead of it being like necessarily an instrument on the telescope that's there all the time, basically certified is that you can take this to different telescopes. So basically, we had this in Albuquerque. We drove it to Flagstaff, which is about a 4-hour drive or so. And we got there, we took it in, aligned it, made sure stuff we get moved around in transportation, put it on the telescope, and then that night we were getting basically results of it. And basically, we were able to close the loop at 30 hertz. Using basically our own wavefront sensor and our own reconstructor. We're using the Dalsa camera. We recently switched over to a Loper camera, which has better sensitivity. For the tip tilt mirror, we're using a PI tip tilt stage, and we're using a OKO 37 deformable mirror. Right. Some of these are basically devices that we've been using and have access to. This was the dual frequency device, in which the aperture is about an inch diameter there. This is OKO 37 element device that is mounted on a tip tilt stage, so you can have the tip tilt and the DM actually on the same stage. This diameter of this mirror is about 15 millimeter diameter, and this is a 57 element locator device that has a diameter of 30 millimeters. And this is a device from Sandia National Labs. And it's 61 elements, and each of these mirrors basically can be electrostatically controlled. They give you a piston and tip tilt. And we just started working with that device. Now, the test bed that we have in our lab basically is started testing our lightweight telescope that we've obtained. Basically, it's composed of two main parts. One is an aberration generator, so we can simulate any type of aberration we want, including atmospheric type aberrations. And then we have the AO side where we have two wavefront sensors in parallel. The reason we have this is we have the Dawson camera that we had before, that we can put whatever new type of wavefront sensor we want to try. And then we have the new camera that we have basically with our Hartmann wavefront sensor. And so we can put them side by side and test different wavefront sensors with it. And then as far as the correction, we have our MEMS device that we have applied on the tip-top mirror. And so this is the device that we're using to generate the aberrations, commercially available HoloEyes device. We're using it, basically, it doesn't have 2 pi, it basically has pi through, so we're using it as a binary device. And looking at one of the diffractive orders to basically get the aberrations generated that we need to our system. So basically light comes into the device, and it's in a mirror, goes through a couple of lenses, and then gets injected back into our AO system. This basically is just showing a little GUI that we have to control. The way the device works is we basically send it an image of what we want to apply on the LC. And so, okay, the screen's in basically this position here. So we're using like a dual monitor system. So we have the image sent out depending on how you set up your system. You set up the X and Y position, so you set out and you send out the image. And then with this, basically you can generate Zernikes, or you can generate atmosphere, however you want. And then when you generate the atmosphere, basically it does it with the Zernikes. And basically this is the way the coefficients are being changed over time, so we can simulate the atmosphere and the wind propagating. And this basically is just showing some simulations of what is being sent to the LC device for different DORMs, for different, we can simulate different telescopes that would be inputting into our system, different diameter and different atmospheric characteristics. Right, now, what we've done is we put one of these MEMS devices directly on a PI busy instrument tip tilt stage. So we can do basically the global tilt and the higher order correction on the same device. And basically what we have here is we put the device on the tip tilt stage and then basically fed it a sinusoidal signal varying in frequency, and compare that with just having a standard mirror on there. And we got some interesting results, because basically this is just showing the residual that you get, that you're varying the tip tilt, and then you took out exactly the motion that you would expect to get. This is what would be left. So for low frequencies, we're not getting any residual stuff. But as you increase the frequency, basically the mass of the mirror is actually, you're ending up with some residual motion that's being introduced back into your system. While with the MEMS device, we're getting less of that. So it's a good thing. Right, now this is an example of a test bed where we have an aberrated wavefront that we put on, and then we get the correction. And this is basically just showing the simulations for the simulations of what we would expect to get. So basically these are the aberrations with these coefficients on the Zernikes. And this is what we actually get in the experiment. And this is the corrected PSF that we get. And this basically is showing the system operating open loop and then closed loop. and with X and Y crosscuts. And this is a comparison of the open loop versus closed loop, looking at the Strehl ratio for that system we just came. Now, basically, for apertures, basically much greater than or not, you need to use adaptive optics. And the main reason we're looking at adaptive optics is we're going to eventually be using it on an interferometer. Basically, this has never been experimentally demonstrated, so there's a lot of issues that we have to deal with and see how effectively this is going to work. And this is in Flagstaff, Arizona. Basically, it's showing the naval prototype optical interferometer here. And what we want to do right now, what they have on there is just flat mirrors, stereostats, basically. And they can get very nice high resolutions on very bright objects. Now what we want to do is basically put telescopes in there instead of just the flat stereostats. But to do that, we're going to need to add adaptive optics to the systems. So our goal is basically to be able to look at much dimmer objects that we can now when we put these telescopes with adaptive optics on. And so one of the other parts of it basically that we're doing is we're doing some development in carbon fiber reinforced polymer telescopes. We want lightweight telescopes that we're going to be able to put there that are 1.4 meter diameter and be able to move them around. Basically, this is a material comparison that Sergio has where he's looking at different types of materials that are used for glass, and what density, what different characteristics you can get. And what's nice about the CFRP is that you can vary these characteristics depending on exactly the way you layer the materials. And here's a couple pictures using the CFRP mirrors. And the really interesting part about these mirrors basically is that a traditional mirror made out of glass takes, especially on the order of large diameter, 1.4 meter or larger, takes months and months to basically make that mirror. Whereas with these, basically, once they have the mandrel made, basically they can just layer the material on it and within a week's time pull it out and have a working mirror. And these are some examples of what they've been able to do with a 16-inch CFRP mirror. Some basically pictures, astronomy type pictures, and then some longograms showing how the surface quality is. And here's a picture, you remember Sergio's picture of Sergio holding basically the primary mirror for this 1.4 meter diameter telescope. And the entire basically optical telescope assembly is going to be about 250 pounds on a 1.4 meter diameter, which is, I mean, if you don't know about telescopes, it's really amazing. Basically, here he's showing basically the history basically of what the aerial density of the mirrors. Basically, for a long time that changed. People just did the standard same thing, basically out of glass, solid pieces of glass. So they're very, very good at and now basically people have started lightweighting the systems, and this basically is where our telescopes will be. And just basically to summarize this, basically adaptive optics basically is a mature technology that DoD's been doing since the 70s. However, it's very expensive, so with the new emerging technologies with MEMS and liquid crystals, there's potential to where more people will be able to have access to be able to do adaptive optics. Not necessarily just on telescopes, but also to actually be able to do on other optical systems. Basically, the liquid crystals and the MEMS, I think, are the big things in reducing the cost. Let's see. I think I have a little more time just to talk to you about some of the other work that I did before I joined researchers that I think is actually relevant. That's the real-time holography with liquid crystals and devices. And see, can I just play it on the board? So basically, you have a liquid crystal device, right? And then you have a reference beam radiate here, and then you have basically another beam here coming in. And this beam basically, if you've sampled your aberrator, basically it's the atmosphere or whatever it happens to be. Basically, you form this interference pattern. Basically, and it's going to essentially form this interference pattern, topographical map of what the aberration is, right? And then if this is an optically addressed device like the Hamamatsu PAL device, which basically uses an optically sensitive material here, which changes these light intensity, basically variations, into a voltage. And then you have a liquid crystal layer in here, which now basically will change basically its index refraction depending on what that voltage difference is. And you bring a beam down here, it's gone to that same basically sampled atmosphere. When you come off the liquid crystal now, this aberration has been corrected. And what's really nice about this technique, this real-time holography technique, is that you don't have to use a computer system like the traditional adaptive optics. And that's why I think you guys would love this conference and hear about is light basically activated with the crystals. And so this type of technique I think is really interesting for that. Yeah.
You showed one of your earlier slides, the liquid crystal device with, I think you quoted a 30 hertz frame rate, refresh rate. I'm just wondering, is that actually fast enough to do what you need to do, or do you need to go to much higher frequencies to account for aberrations from the atmosphere?
Yeah, the atmosphere typically is somewhere around the green frequency of time lapse, so basically ends up with stuff around that. More in the 100 hertz type of range. So it isn't fast enough. That's why they went to use the dual frequency device, which they were able to improve the speed up to the point where on good sites and good nights, basically you could actually use that device to do correction. So the 30 hertz device that we're using to do basically the commercial device that we were using to try and do atmospheric correction. With that device, you can do it, it's too slow.
So the dual frequency device that's up in those.
Yeah, it's better. Like I said, on good nights and good conditions, you can get it to work really well. Okay,
So this makes us do that.
Any question? These Zernike polynomials that are used in the test bed and create, is there any intent when you're actually using these adaptive optics? I mean, how do you determine how to adjust the adaptive optics element based on what you see? It seems to me that if you knew that the object in question was a point source and it arrived at this mess, then you can unconvolute it. But if what you're looking at is, say, a galaxy or a nebula, it seems, how would you decide?
Well, what you do in that case is basically what people do, right, is they use it's called basically a guide star, a natural guide star, right? So you basically have a star that's bright that's next to it. Basically, you use that, and then as long as you're in the isophonatic angle, basically you correct for stuff around it as well. But as long as you're within that isomagnetic angle, you can get correction for the galaxy, basically, as well.
And apparently it's good enough?
Yeah. Well, not necessarily, right? That's why basically people have also gone to using laser guide stars, right? Because there isn't basically a bright enough natural guide star everywhere in the sky you want to look. So if you can create an artificial, basically, star that samples that atmosphere, then you can use that. And the techniques that are used for generating an artificial guide star, you can use scattering, basically off Rayleigh scattering, basically off the atmosphere. But another technique is to use basically the sodium layer, which is much higher up, which is about 90 to 100 kilometers up in the sky. And so basically, if you hit that layer, basically of sodium atoms with the exact right wavelength, you can get it to absorb and then re-emit. So you can create this star basically anywhere in the sky that you want. And you can use that basically to characterize the atmosphere.
And now there's one more question. The task of telling the adaptive optics element how to form, do you use these Zernike polynomials to describe the kind of aberration you need?
It depends on exactly what you're reconstructing. I mean, there's a lot of different ways that people go about doing it. I mean, we have a programmer that came up with his own method that we use on our stuff. But I mean, there's other techniques and conventional ways of doing it. I mean, and it also depends on the device. I talked about using the MEMS device. If you use that with a curvature wavefront sensor, you can get a relationship where it's let's see, remember where it's at. In that case, there's a simple relationship. Here, basically this one. Basically, so it actually depends on the deformable mirror that you're using and the wavefront sensor that you're using to actually measure exactly how you're going to try to develop your reconstructor.
So any other questions?
Has anyone ever looked at using problem stabilized PFCs on network Cs? Because they can switch a lot faster and then threatening power with your previous PFCs.
I mean, as far as the devices, I mean, the liquid crystal devices, I know Strehl did a lot looking at the different devices and what you could actually get. Some of that's the problem is actually being able to get devices made and physically put into our hands to be able to try to work with them. Because, like, I mean, especially with liquid crystals, a lot of times when you try to go to a company, they have, you know, the big money stuff is on displays and doing amplitude modulators instead of doing phase modulators, which are different that people don't want to stop, you know, what they're doing basically being, you know, one or two devices per us. So it's been difficult trying to get devices specifically made for what we want. And like the devices that we did have, we got under government basically called the SBIRs, so basically allowed you to work with a company and give them a certain amount of money to actually develop a device specifically for what you have to do. But as far as that, I mean, I don't know for sure if any devices have actually been made with that type of holding person.
So there is also some devices that use magnetic seed
Yeah, Sergio's done some work with those and have another SBI with those where we've got some faster response is with them, but it becomes an issue exactly how can you use the device, also exactly do the type of phase correction that we're trying to do.
So there was another question.
Thank you, Summer. You described initially the phase aberration as being pupil, but of course it's out of the atmosphere. Is it at all important to have the phase correction conjugate to the atmosphere, or do you just put it anywhere in the telescope?
Well, I mean, what happens there, right, is that when you do have the extended atmosphere, what actually happens is you don't have just the first basically order approach that you're going to do is you're just going to say, well, the majority of the aberration is near my telescope, and that's where I'm going to basically effectively, at that conjugate plane, is running with the correction. But you do get basically different layers and they have different effects. So if you have the aberration at a higher layer, by the time it gets down to the telescope, those phase aberrations actually get turned into amplitude. And so you get simulation effects. So in that case, what you actually to do a better simulation, we would actually have to include more than one phase in our system. And ideally, you'd like to have more than one deformable mirror in your system to try and correct those different conjugate planes and try to measure basically the atmosphere at the different planes and try to correct for those different planes to get a better correction.
So it is important to try to put as much as you can put the corrector in conjugate planes.
Yeah, you want to put your corrector basically at the appropriate place where, and when you only have one corrector, you try to put it basically where the majority of the aberration is being generated, which is typically on most systems is near your telescope.
So, other questions? So let's thank Kai for his talk. So the next talk is from Robert McLeod from the University of Colorado. And he will talk about this photo-induced mass transport.
Can everybody hear me? No? Okay, good. So if you can't hear me, wave and do hand signals.